Welcome to Dynamics. You've been waiting on this forever, so here it is. Our online course for Dynamics, the follow-up to Statics. It's probably one of the hardest courses in engineering and one of the most misunderstood courses. So I'm going to put a series together and maybe this will help you, okay? So here we go. Dynamics basically consists of two portions, a kinematics portion and a kinetics portion. So the kinematics portion is the branch of physics concerned with the geometric aspects of motion, like where a particle is, how fast it's moving, is it accelerating, and all those things are time dependent. The next thing we'll talk about, this will be later on in the series, basically about halfway through, we'll switch over to kinetics and we'll start talking about an analysis of the forces that cause the motion, whether that's a collision or a spring imparting motion or some other thing that's causing the motion. This generally students have not too hard a time with. This is pretty understandable. This is generally where the wheels fall off. So hopefully I can get you through that. But anyway, our whole dynamics course here, what's it based on? Newton's, did I put third law? That's not that right, is it? It's the second law. And what is Newton's second law? Do you remember it abbreviated at least in mathematical form? The sum of the forces is equal to mass times acceleration. I'll put a little vector over that because acceleration has magnitude and it has direction. Okay, mass does not. Now, in all our statics problems that we did before, acceleration was 0, which caused this whole side to be 0. So in statics, the sum of the forces was 0. But not here, okay? So, whole different ball game, all right? So, let's get started and let's start talking about a particle, and we're going to talk in particular about rectilinear motion, okay? So, a particle is moving in rectilinear means, you know, just a XY direction, a linear direction. So, let's just assume we have a particle, I don't know, that moves on a straight path, and there he is, okay? This is the distance S rather. And S is just the location of that place in space, okay? So where is the location of our particle? This is our particle that we're concerned with. Now let's say that particle moves some, okay? It goes from that position to maybe this position. So he moved. Looks like eyeballs, doesn't it? Okay, we'll put a little nose on him. No, let's call that delta S. Delta S is the amount that he moved, okay? So if this is the origin over here, origin, okay, then that over there is his final position, okay? So we'll call that like S prime, which is his final position. So S prime is equal to S plus delta S, or delta S is equal to S prime minus S, right? Either one of those works. That's pretty easy to understand, right? And that's about position of the particle. So remember the position, when we start writing equations, position is represented with S, not X that we're used to. So don't be baffled by that, okay? Okay, so if we know how long it took that particle to move from that point to that point, in other words, how much time, you know, we could calculate like how fast it moved over there, right? Because we know the time and we know the distance. So we could say that velocity is equal to like a change in position divided by a change in time. And that makes sense, doesn't it? Velocity is like, you know, in meters per second. So I'm moving so many meters per second. Some distance over time. You know what we can do with this little delta S? We could subdivide that into an infinite number of little tiny delta S's. What would we call those? Do you remember back from calculus what we call those tiny little delta S's? We would call those little differential S's, right? Every one of those little strips, remember in statics there are little differential areas? There's differential distances divided by those little differential times that go with that, okay? So yes, there's going to be some calculus in dynamics, okay? And so what we come up with is this relationship here is that velocity is equal to ds over dt, okay? And again, the units for that might be something like meters per second or feet per second or feet per minute, you know, some kind of a velocity unit there, okay? So also if we know the velocity at 2 points, which means like we knew how fast it was moving there and we knew how fast it was moving there, then we can also calculate how fast it accelerated or it changed, you know, the change in velocity from one point to the other. So we could do this, we could do it by the same token, we could say acceleration is equal to a little delta velocity, a change in velocity over that same change in time, right? How much did the velocity change over some period of time? And again, if we started looking at little differential velocities in between there, right? We could get an equation that looked like this, that A was equal to dv over dt, okay? By the same way we got this equation here. Now this is kind of a biggie, okay? We'll put a little box around him. And this one's going to be in, what is this? It's going to be in meters per second over time, so we get an extra time in there. So it's going to be like on meters per second squared this time, or feet per second squared, right? For the units for that guy, okay? So there's our next biggie equation, is A equals dv over dt, okay? Now that's a biggie. Now let's just, for instance, let's do one more. Let's get one more. Now this is not going to be a new equation, but it's going to be one we can get from this. Let's solve this guy for dt and this guy for dt. So we get, what does this one get? Dt is equal to, move that over there, ds over v, right? And then this one would be dt is equal to, move that over there, dv over a. And then we could set these two dt's equal to each other and we'd get this. ds over v is equal to dv over a. And then let's just solve that out, move that over here, move that over there, so we get this. A ds is equal to what? V dv, right? Okay, so that's kind of another big handy equation to have that relates acceleration to velocity, okay? So these three are biggies. Let's put them over here, and as I go through the videos, I'll leave these equations over here so you can kind of see, remember those equations and follow along here. So these are the big ones that we've got so far. We've got V equals ds dt, and A is equal to dv dt, and then this guy right here, A ds equals v dv. Now we don't have three equations here, gang, okay? Yes, there's three equations, 1, 2, 3. But this guy right here was just a substitute. There was no new information here, right? This one was derived by just substituting these two. So I can't like say, oh, I can solve for three unknowns now because I have three equations. I really only have two because I just substituted one into the other, okay? Now, we're going to take these equations and we're going to do a little integrating, and we're going to see if we can come up with something. Now, one of the things about these equations is this acceleration from that point to that point was constant. That's important, okay? And if we use that information, we're going to be able to derive some new stuff. So let's erase this and let's keep going here, okay? So let's get rid of all that. Okay, so all we're doing is kind of introducing this rectilinear motion and kind of coming up with some equations that we can use to solve some simple dynamics problems, okay? So next, let's take that equation and let's just see if we can integrate that. Now remember, this is important. This is important. This is for constant acceleration. That's important, okay? So let's take that equation. A is equal to dv over dt. And let's just, let's get rid of the dt. Let's move him over to the other side. So we get dv is equal to a times dt. Okay? Now to get rid of this, let's integrate, get rid of the little differential there. So let's just integrate both sides. Now this one we're going to integrate from 0 to v. We're going to assume that this velocity was 0 when it started off, and there's this final velocity, right? And on this side, we're going to assume this. Time was 0, and there's our new time, okay? So we're going from 0 to t over here, 0 to v over here. And we're going to get this equation, we integrate this. This we're just going to get a constant, right? Just v, okay? And on this side, what we're going to say is we can get a v0 because remember, at time 0, our v was 0, okay? And then that is going to turn into what? A is just a constant. So plus a, and we'll put a little c there to remind ourselves that that's not just any acceleration, it's constant, okay? Times t, right? We get a t in there. So there is equation number 1, okay? And that is going to be velocity as a function of time, okay? So this guy right here is velocity as a function of time, okay? So let's write that guy over here. This is an important one here. So v equals v naught plus a t. That's a biggie. Okay. All right. All right, next let's do the same thing. Let's take this equation here and let's see if we can integrate this one. So we've got v is equal to ds over dt. You know what? I know what v is equal to. I just solved for that. So let's do this. V naught plus act, and then let's move the dt over to the other side. So dt equals ds, okay? Again, let's integrate both sides. This is position, and this is time, right? So this is going to be from 0 to the new position s, and this guy is going to be from 0 to time t, right? So this is a change in position. So what we're finding here is position as a function of time, okay? So we integrate this, we're going to get a new equation. This is a good one. Okay, this side over here is just going to give me s, okay? And this side over here is going to give me s naught, which initial position again was 0, right? Plus v naught, and if I integrate a constant, he gets a t on the end of him, doesn't he? Plus, what's that going to be? A constant t squared divided by 2, right? Or we could put a 1/2 out in front of there, right? Because the t is going to give me a t squared over 2, isn't it? Bam, there's another equation. That's a good one. So again, this is position as a function of time, okay? Position is a function of time. Let's put that one over there. We'll put a star by him too. He's a good one. So s is equal to s naught plus v naught t plus 1/2 at squared. And again, I'll put a little c there because that's constant acceleration. We call these the constant acceleration equations. Now from that, if I take this equation here and I solve it for t, and I take this equation here and I solve it for t, and I plug that equation in for that equation for t, I can get one more thing, and that would be the final equation. It would be velocity as a function of position. So this one is, the last one is velocity as a function of position. And that equation goes like this. V squared equals V naught squared plus 2a, constant acceleration, times s minus s naught. Okay? So there's our last equation. And again, this is not a new equation. Okay? This is not a new equation. This is just that equation plugged into that equation, okay? So, but it's handy to know if I know velocity and I know position, then I can solve for maybe acceleration. So knowing different things, it's just a simplified version. So we'll put it up here as our third equation, even though again it's not really a third equation. So v squared equals v naught squared plus 2ac times s minus s naught. Okay? So there you go. There's the constant acceleration equations derived. You know, where they come from. These are the biggies, okay? There, and there. And then this is, I just got rid of the differentials over there, right, by integrating. And we got these here, okay? You know what we're ready to do? We're ready to start working some example problems. So the next video I'm going to show you some example problems, and we're going to put these equations to work. Thanks for tuning in. I'll see you next time.